Hello and welcome to the final video in our series on convection. We're going to address a topic that's very important for nuclear engineers, convection in rod bundle geometries. Now, in nuclear engineering, rod bundles represent nuclear reactor cores and steam generators and things of that nature. They also can occur occasionally in other fields. Now, they do have some unique properties. They have a little bit of a unique shape, and that typically results in improvement in heat transfer over a similar geometry circular tube. So we have some enhancement of heat transfer. And our typical approach is to use the Nusselt number for circular tubes, or Nusselt number sub CT, and then modify that to find the Nusselt number for the rod bundle. Typically we'll use the Dittus-Belter correlation for the Nusselt number in a circular tube. However, other correlations are going to give pretty reasonable results. The next step then is to determine the enhancement factor, and we rely on empirical models to do that. So we have different models with varying levels of complexity and range of applicability. You can see the Presser model is a little bit more complex in form, but it has a wider range of applicability. The Weissman model is a simple linear model, so it's easier to use, but it has a more limited range for applicability. And both of them are going to depend here on the pitch to diameter ratio. So if you have a rod bundle, you have the diameter of each rod, and then the pitch is the distance between them. And you can have a square array like this one, or you can have triangular arrays of rods. Those are the two most common structures. You can also look at a little bit more detailed analysis. If you look at all of the subchannels surrounding a given rod in the bundle, instead of just looking at this one piece, you have to look at all of the surrounding subchannels. Or if you have something that's not a regular geometry, you're looking at all of these surrounding subchannels. So our hydraulic diameter is going to be based on the sum of the flow areas and perimeters. And once we have that value, we can get the Reynolds number, Prandtl number, and so on. And we have this, again, it's a little bit more complex functional form than the Weissman model, but it's designed to work for a wider range of conditions. So you have the Reynolds number behavior, the Prandtl number behavior, and then there's a geometrical parameter that depends on the pitch to diameter ratio. The error for this correlation is only about 8.5% for a pretty wide range of conditions, so it's pretty reliable. Another important topic in nuclear reactors and nuclear heat transfer is liquid metals. Liquid metal coolants are sometimes used in nuclear applications. They have a high density, high heat capacity, low vapor pressure, and high thermal conductivity, so they have some major safety benefits for some of these nuclear systems. In this type of behavior, liquid metals, conduction is the primary heat transfer mechanism, even in highly turbulent flow. The reason is because their Prandtl number is very small, 0.01, which means their conduction is much bigger than their momentum diffusion. So typically, we end up using the Peclet number to characterize liquid metals. The Peclet number is just the Reynolds number multiplied by the Prandtl number, and it scales conduction to convection. So we can look at a few very simple cases. If we look at a cylinder in liquid metal, so we have a cylinder and the liquid metal is flowing across the cylinder, we have a correlation. You can see here it's a constant times Peclet number to a power. So it's not so much different than some of the other Nusselt number correlations that we've seen, where it was constant times Reynolds number to a power times Prandtl number to a power. We can also look at this model for a sphere in liquid metal, and there's a little bit of a difference here. There's a constant plus the Peclet number term, and this is a very, very common form for liquid metals. The constant accounts for what happens when there's no flow. So in this case, if there were no flow, the Nusselt number on this sphere would be 2. Which happens to be the same as you would see if you actually solved for the heat transfer problem in conduction in the non-moving fluid. So Nusselt number of 2 just represents conduction out of the sphere with no flow. You can also look at two banks. There was some work done at Brookhaven National Laboratory, and you could see the constant and the Peclet number term for that as well. Now we can also look at internal flows. If you have flow in a pipe or some kind of duct, you want to use the Skupinski correlation if you have a uniform heat flux on that duct, or if you have a uniform surface temperature, you're looking at the Sibin and Shimazaki correlation. Again, rod bundles are very important for nuclear applications as well. So if you look at the Kazemi and Corelli equation, you have a constant, and then you have a pitch diameter and Peclet number term, and then another pitch diameter term. So this was developed for a wide range of conditions. You can see from the graphs it works better for some conditions than others, but none of the correlations is particularly good for all of the conditions. So just keep in mind other correlations exist. Some are better than these correlations, but they're also more complex and more difficult to use. So if you're doing a bunch of design work for a particular application, you don't want to just rely on this very limited set of empirical correlations. You want to go out and find empirical correlations in literature that match the work that you're trying to do and that are more applicable to the particular application. However, this set of correlations will be useful for the problems we're going to be doing in class.